This morning, Luis will tell us about Chow functions for posets.
Okay, morning, welcome. Thank you for coming to the last seminar before the break. So as Jun said, the title of my talk is Chow functions for partially ordered sets. This is based on a preprint that we put out last month with Jacob Mathern and Lorenzo Vecchi. The title of the paper is the same title as the talk. You're welcome to take a look if you have, interest in this. And I want to start by mentioning one slightly imprecise but catchy phrase that triggered all this research, which is that the Hilbert series of a matroid Chow ring arises by inverting the reduced char poly, the reduced characteristic polynomial, in the incidence algebra. So this is the quote that started all of this. This is actually a statement that can be formulated very precisely. We will do so later. And the idea is that in general, computing a ring and then its Hilbert series is very expensive. So having this as a shortcut seems like a perhaps more combinatorial way of thinking about that Hilbert series. Okay, so let me start the actual talk by saying that by fixing some notation. So throughout this talk, I will have a finite graded bounded poset which means that, the part of being bounded means that there is a single element 0 hat, which is the only minimum of P, and there is a single element 1 hat, which is a single maximum of P. And that is this thing. Graded means that, well, if I take the function rho given by, it takes an element of the poset that gives me a non-negative integer. This is often called the rank function, given by rho of t equals the length of any maximum chain from 0 to p. This is well defined. So in particular, all the maximal chains have the same length whenever I fix the bottom to be 0 hat and the maximum to be the element t. And with this setup, which arises quite often, one can define an algebraic structure called, actually, without even having this, you can define something called the incidence algebra. So in case you are not familiar, I will say very briefly what this is, but essentially the incidence algebra is associating to every interval in the poset some polynomial or some object in some ring. For me, it will be the ring of polynomials, so I will write that up. So what this is essentially that I am taking the free set X module over all closed intervals of P. So I have a finite poset, so I have finitely many closed intervals. To each interval, I can think of as a coordinate, and I can have polynomials for each of these coordinates, and the polynomials will always have this variable x. So whenever you see an x, you have to think that's the variable that I have in my ring of univariate polynomials. So in particular, I say that because t will always denote elements of the poset, and x will always denote variables of polynomials. And yeah, so in case you want to know this precisely, the product of two elements A and B in this instance algebra is given by. So I have to tell you what the product is at each closed interval. So I will tell you AB at the closed interval ST is by definition the sum over all the elements that lie in the interval. And I take, like, so if my element is W, I will take the interval that goes from S to W, and then I will compute the polynomial in that interval coming from the element A, and I will multiply with the corresponding polynomial for B, but for the upper interval. So this is a product in the incidence algebra, and you can prove various things, like, for instance, that this operation is associative, and I mean, there are more desirable properties that this structure satisfies. One important property is that you have an identity, so you can talk about inverses. So let me write that. So remark. The element delta in I of P given by delta ST equals 1 if S equals T, and 0 if S is smaller than T, is a two-sided identity. So you can check very easily that if you multiply A with delta, you obtain A, and if you multiply delta with B, you obtain B. So this is the identity in this instance algebra, and with that you can think of you can like conceive the notion of inverses, and there is a very easy criterion to check whether an element has an inverse. So just in case you are more inclined towards linear algebra, you can think of the elements of the incidence algebra as being matrices whose rows are indexed by the elements of the poset, whose columns are indexed by the elements of the poset, and whose entries correspond to, like the entry AST would correspond to the polynomial in row S, column T. And the fact that this is defined only for intervals of the poset will tell you that your matrix is upper triangular. And this product is actually the product of matrices. And yeah, this is just the identity matrix. So makes sense. And now one cool way of seeing that this proposition that I will tell you is that when would you expect a matrix with polynomial entries to be invertible, an upper triangular matrix with polynomial entries to be invertible? Well, only when the diagonal has invertible elements in set X. So you would expect that the matrix has diagonal elements that are only 1 or minus 1. So let me write that. Remark. An element A in I of P is invertible if and only if ASS is the polynomial plus or minus 1 for all S in the poset P. So this is a very easy criterion to tell whether an element has an inverse or not. Okay, questions so far? Yeah.
What are the compatibility conditions between the polynomials in the different entries of the upper triangular matrix?
Appearing, there are not, I mean, you can have arbitrary polynomials. So this is like the general setup. So the matrix, so for every pair of comparable elements, you have some polynomial, but later we will add some restrictions and we'll get more structure. Yeah.
I'm still not quite getting the definition or concept of the incidence algebra. Do you take all upper triangular matrices with entry in Z of X or certain matrices?
So more precisely, the incidence algebra is the free set X module over all closed intervals of the poset P. So you take P, you take the set of all closed intervals, take the free set X module spanned by those intervals, and now define the product as this thing. This is the object. Now, if you want to think of these elements as matrices, what you can do is you can label, so you can take matrices that are square, whose rows are indexed by element of the posets, whose columns are indexed by elements of the poset, and you will have 0 whenever the column S is not smaller than or equal than the element T. So AST is set to be 0 whenever S is not smaller than or equal to T. And you have an actual polynomial whenever that comparability relation holds in the poset. You can prove that, well, it's immediate from this definition that this will be an upper triangular matrix, and you will have some zeros, of course, in the upper triangular part. You will have some, entries forced to be 0. But otherwise, you can have arbitrary polynomials a priori.
First step there is we need a linear extension of the poset.
Yeah, you can do that.
But otherwise, the matrix will not be upper triangular if you wouldn't.
Yeah, of course. I am thinking of yeah, that's right. More questions so far? Like any other? Okay.
Guys, can I just delve in? I think I don't understand anything more than before.
Yeah.
So let me ask again. If you have this pre-algebra generated, what's the role of X? I mean, this looks
there's no a priori, so you can have any ring here a priori.
Okay, so
So there's no actual. So that's why I didn't put so much emphasis on this part. You can do this over any ring, and of course the theorem here will change a little bit. You will have that an element is invertible if and only if the diagonal elements are invertible in the ring. But otherwise, you can define this. Actually, in EC1, Stanley defines this for an arbitrary field, but this carries over any ring actually. So
thank you.
Yeah. So the moral here is that for every closed interval of the poset, I have a polynomial, and that is something that will be like very instrumental later. But before moving towards examples of posets and incidence algebras, let me now indeed put a restriction on the type of polynomials that I can have for every closed interval. So this is the first time we will see like the function rho appearing here, because in the definition we didn't mention rho so far. So and here, so define I rho of P a special subset of I of P by all the elements in the incidence algebra, so all the elements in I of P, such that the degree of the polynomial associated to every interval is not too large. And by too large, I mean that this is always bounded by the length of any maximal chain that starts in S and ends in T. So if I have an interval that has a rank 5, I will require that my polynomial has degree at most 5. That's a requirement I will do. In the previous definition, in I of P, I can have a polynomial of degree 1000 you can have if you want. But now I will bound all the entries. And so having this allows me to define an involution in this set. An involution is pretty easy to see visually. So
I'm just a bit confused why we put S strictly less than A then.
Sorry, I think where I want to be. Right,
Degree is also degree as polynomial in X.
exactly.
So now it's
Exactly. That's why I want polynomials. Okay, so there's an involution in this special part of the incidence algebra given by every element will be mapped to an element called a rev, and precisely a rev at the interval st is just a st. So let me put the variable here so that you can remember that this is a polynomial. So what this is doing is just this just reverses the coefficients. So what I am doing is for every interval, I will take my polynomial reversed. And the reversing is done with respect to the maximal possible degree. So even though the entries are bounded in degree, so you can have an interval rank 7, whose polynomial has degree 3, when you reverse the coefficients, you will have to do it with respect to the degree 7. Okay, so once you have these, well, you can see that this is indeed an involution. So if you apply it twice, you get the same thing you started with. And yeah, this is something that enables us to define very important kind of elements in the incidence algebra that Stanley called kernels.
IFP was a ring. I know P is a subring or an ideal or what?
It's a subalgebra.
So when S is equal to T,
Yes.
then the right-hand side is less than equal. Okay.
Yeah.
So
You must have constants. That's yeah. So this is the following is a key notion. So this is a definition due to Stanley. So a P kernel is an element kappa in this I row of P such that, okay, so kappa to the -1 exists, and actually kappa to the -1 is just kappa reversed. So this is a very, very strong like condition on an element. So kappa to the -1, well, you can think of as the inverse of a matrix in a certain upper triangular matrix. And this is telling you that, well, inverting that matrix has to just reverse every single entry coefficient-wise. That looks like imposing lots of equations to be true. So a priori, one would think that having a kernel is very rare. So that there are no like, I mean, there are no, a priori, there's no reason to expect that there will be many kernels. I mean, of course, there could be like some trivial ones like the identity, but if one wants to think in more interesting examples, it's very tricky to get convinced that something like this could exist a priori. But the thing is that these things are quite pervasive. So
the identity doesn't work, right?
what, sorry?
Identity doesn't work.
The identity, yeah, doesn't work because, yeah, that you're absolutely right. Yeah, the identity doesn't work. Yeah. Yeah, if you put the identity, so you're reversing every entry. No, that it does work. It does work. Yeah. It does work because you're reversing with
zero.
Yes,
okay,
yes,
okay,
yes.
okay.
Yeah,
It doesn't
yeah.
big degree.
That's right. It does work. I was confused because I think I remember writing that down somewhere. So yeah. Yeah.
that kernel is a subgroup of the multiplicative group.
I don't think so. I don't think so, but I don't know immediately. I have to think about it. But okay, so let me just add one extra word that is borrowed from a paper by Nick Proudfoot. He uses this term for a slightly different thing, but it works just the same way. So we say that kappa is non-degenerate if the degree of kappa st is equal to rho t minus rho s for all s smaller than or equal to t. So I will say that the kernel is non-degenerate if every single entry of my matrix kappa has the maximum possible degree. All what I'm going to say works for any kernel, but this will allow me to have statements that look more neat afterwards. So I will want to add this assumption sometimes.
Are you gonna do any examples at some point?
Yeah, that's what comes up right now.
Thank you.
So this is actually 3 examples. So, well, this is to me a very a very interesting fact. So let me give first example of this. For all graded bounded P, the element kappa equals chi, the map so for all of them is a picker. So what I'm saying here is the following. So take any graded bounded poset. So take any interval. You can define for every interval the characteristic polynomial. So the characteristic polynomial will just be like if you put the Mobius numbers and then sum for every level the Mobius numbers and collect those into a polynomial. Well, that's the characteristic polynomial. If you do that for every interval, this map is a picker. And the proof of this is not trivial, but in the end, it's just a reformulation of the inclusion-exclusion principle. So this is equivalent in a certain way to the inclusion-exclusion principle. And yeah, so whenever you have a graded bounded poset P, you can associate for every interval the characteristic polynomial. Well, that's a kernel. And that's surprising in my view, at least. And yeah, this is just one example. In the case of matroids or hyperplane arrangements, one has an interpretation for this polynomial that comes from geometry, but you can certainly define it in the same way for any graded bounded poset. And that will be very useful later, because even though we will not have any hyperplane arrangements nor any geometry a priori, still we can draw or obtain many conclusions that arise from the work of June and collaborators. Okay, so this is one example. Let me give you another example.
To make sure I understand what characteristic polynomial means here. This is the generating function for the poset?
Yeah. Do you want me to write that down in case?
I'm just used to I've never heard this characteristic polynomial
Okay.
used for this. I always heard for a matrix acting on a space and.
Yes. Okay. I see. So you are more okay. You are more. Your mindset is more geometric. So let me define it combinatorially. So for every interval ST, define recursively mu st, this is a Mobius function, as 1 if s equals t, and minus the sum over all elements that lie above s but strictly below t of mu sw. So this will define a number for every interval. That's a Mobius number of the interval, and then define chi st. This is a polynomial in the variable x. I will write it just so you remember that. So this will be the sum over all elements w in the interval st of mu sw times x to the row of t minus row of. So that's the characteristic polynomial of an interval in a great bounded poset. So you see here that I don't require any geometry at all. So in case you want to see an actual computation, let me
Chi has some index there, or
chi, sorry, this is x. Yeah, my x's and chi's are similar. So yeah, I mean, let me.
So, sorry. So mu here, thinking mu in the incidence algebra is the inverse of the function which takes every interval to 1.
That's right. That's right. That's the fancy way of defining it. So in case that you want to, so let me reformulate what Alan said. So take the element zeta in the incidence algebra given by all ones. So every interval has a 1. Well, that's an invertible element because of this condition that I wrote here, because in the diagonal of my matrix I see 1s. So this element zeta has an inverse. Well, that mu is precisely the inverse of zeta. And what this is just if you want to like be very like fancy, you can write chi as mu product this element zeta reversed. So this is what this is. Yeah, this what I wrote here is just a reformulation of this. So mu is so this is one definition, and this is another definition. Okay, so this is one example.
Sorry, I don't understand that. So mu is a matrix.
Yeah.
Chi is a single polynomial, yes?
And chi
is
is an element of the incidence algebra. That
Chi st is, yeah, okay. Got it.
This construction will always produce kernels. There's nothing fancy. Yeah.
yes, that's another very cool theorem by Stan. But yeah, I won't get into that direction yet. Okay, so that's one example. So in particular, these examples lead to a very nice theory that I will tell you something about briefly. But there are many more examples, and actually these other examples are what motivated Stanley in the first place. So let me erase this.
formula that you wrote down is basically also proves that
What, sorry?
chi equals mu times zeta reverse actually proves your first example. Is this right?
Yeah. I mean, many people are, with considerable experience working with instance algebras, like to define things like this, but I prefer to be more explicit with what mu is with this recursion that you might have already seen before.
So what's the ref of the product? That's a very basic question.
What's the rev of the product? It's so rev will, so A times B rev is A rev times B rev.
Ah, okay,
Yeah.
okay, so it's
Okay. So another example. So I'm continuing with examples. So yeah. So example number 2. So whenever you have, if P is the phase lattice of a convex polytope, the element epsilon given, so epsilon in I rho P given by epsilon ST equals the polynomial x minus 1 to the rho of t minus rho of s for all s smaller than or equal to t is a p-kernel. So phase posets of polytopes have always this kernel, which is of course different from chi. And chi has this Mobius function appearing. This is much more easy to see. And actually, so one interesting thing is that there's a notion of being combinatorially invariant, which means that whenever you see two isomorphic intervals, you expect the same polynomials to appear. With the characteristic polynomials, that is indeed true. With that thing, of course it is true, but more is true. Whenever you have two intervals of the same rank, you see the same thing. So that's a kernel with very strong restrictions. But the fact that this is a kernel with very strong restrictions is precisely an equivalent reformulation of being an Eulerian poset. So let me write that. The note. This, in fact, characterizes Eulerian posets. Does anyone, I mean, everyone knows what an Eulerian poset is?
No.
Okay, let me say that. So an Eulerian poset is a poset. So let me write the definition. So poset P is Eulerian if mu st, so the Mobius function, is always a -1 to the rho of t minus rho of s. So essentially, this is saying, if you have some imagination, that every interval of the poset has the same number of elements in odd rank and even rank. So for all st. So all phase posets of polytopes are Eulerian. All phase posets of complete pans are Eulerian. All phase posets of regular CW spheres are Eulerian, and so on. There are many examples. Eulerian posets form a very complicated class of posets. So don't be, misled by thinking that this condition is so strong that the class of posets is like easy, because that's not the case. Yeah, but satisfying this property is equivalent to having this epsilon as kernel. So that's a good thing to have in mind. And one more example, kernel. So, and actually this is in some sense what motivated Stanley in the first place, together with example number 2. If P is is the Bruhat poset on a Coxeter group, and kappa st is given by the R polynomial, the R polynomials So I won't define what an R polynomial is. This is not an example that I will do in detail, but in case you already know what this is, well, this assignment is a PR.
Is it done to Jerry?
Yeah. Our polynomials always have. Yeah, so in the three cases, actually, the kernels are non-degenerate. And more so, they always, in the three cases, give you monic polynomials. That's even stronger. So characteristic polynomials are monic, x minus 1 to the something is monic, and our polynomials are monic. So, yeah, these R polynomials are defined using the Hecke algebra of Coxeter group. So let me skip that part and just say that this will work in case you are familiar with this construction. And there are many more examples. There's one more very striking example due to Nick Proudfoot that actually produces a kernel on geometric lattices. But then you have to just be more flexible about your definition of rank function. So because of that, extra generality, I won't give you the details now, but it is possible to define another example on geometric lattices that is also relevant because it has to do with H vectors of broken circuit complexes. And I know that some of you are interested on that. So yeah. Okay, so let me tell you a theorem by Stanley that is essentially one of the reasons he actually introduced all this terminology. So this is Stanley in 92. So let kappa be a P kernel. There exists a unique element F in I row of P. So for each kappa, there is a unique F such that the first thing is that FSS, so this is a polynomial for a singleton interval. This is always the constant polynomial 1 for all S in P. The second condition is that the degree of FST is at most rho of T minus rho of S half for all S smaller than T. And finally, that reversing F is the same thing as multiplying kappa with F. So this is called the right Kazhdan Lusztig Stanley function of associated to kappa.
Also by placing the third condition.
Exactly. So let me write that in color. So Stanley didn't actually care about size. So he actually defined only this thing. But then Nick Proudfoot noticed that, well, actually it was Brenty, and then Nick Proudfoot wrote it down like very carefully, that here there is a choice involved. There's no reason to prefer to multiply kappa to the left. You can say, okay, let me define an element G here. So let me keep the previous element F. And so there is a unique element G as well, such that the same condition holds here. So GSS equals 1 for all S here. The degree of GST is also bounded here, but I will require that G rev is G multiplied with kappa to the right. So you can do the same thing. And G and F are not the same thing. And they behave quite differently. And that is what you would call the left Kazhdan Lusztig Stanley function. So the point is, long story short, you give me a kernel, there are two special elements, f and g, small f and small g. F is called the right Kazhdan Lusztig Stanley function, and g is called the left Kazhdan Lusztig Stanley function. Yeah.
Just like a super technical question, but for this to be true for a general P, do you need the element 2 to be invertible to prove existence? I mean, in all these examples, it's fine, but
I am not sure immediately. So
Two is just the degree, you're just dividing the degree, so it's.
no, I meant in the base ring. So
I'm saying that, yeah, okay, I don't see any division by two here, is I guess.
no, it's not in here, I'm just
Okay,
saying.
okay.
Like, you need to go from C, adjoin X, it's like adjoin a half.
I am
down
not-
T.
I don't know the answer immediately.
Anyway, it doesn't matter. But
Yeah. So as I was saying, yeah,
How are Kazhdan Lusztig involved in this story?
that's my next yeah. But before moving to that, so the key observation here is that you have a kernel that produces two very special elements, f and g. So is that clear? It doesn't matter how f and g are actually constructed. The actual construction follows from this recursion. So this recursion involves a small miracle happening, yeah. But the point here is that you give me kappa, if it's a kernel, then I can construct f and g, and they satisfy these degree bounds and this recursion f rev equals kappa f and g rev equals g kappa. So this is the theorem by Stanley. So now I will tell you very briefly for the three examples of kernels that I have told you what f and g are. So that will explain a lot about the main Kazhdan Lusztig Stanley. Yeah, I can erase this part. Yeah, actually, I will give you just one example first, and then I will. I propose we have a small break. So. So. If P is graded bounded and kappa is the characteristic polynomials, so the first example that I told you, well, GST is identically 1. So this is trivial. So I don't claim that the proof of this is trivial. I claim that this is a trivial Kazhdan Lusztig Stanley function. So the left one is trivial. But FST is very complicated. In the case P equals a geometric lattice, F is associating to each interval ST the Kazhdan Lusztig let me continue. I will continue there. The Kazhdan Lusztig polynomial. I think I can maybe erase this part. Yeah. So let me say what about the right. So what this is doing is associating to every interval ST, the Kazhdan Lusztig polynomial of the matroid corresponding to the interval ST. That's I mean, geometric lattices are lattices of lots of simple matroids, and the intervals st correspond to matroids as well, and you have a notion of Kazhdan Lusztig polynomial for matroids, and that's precisely that assignment corresponding to F. So, in particular, you can deduce various positivity properties of F from the papers by Braden, Hu, Proudfoot, Mathern, and Wang. So yeah, let me continue what I was writing there. So the Kazhdan Lusztig polynomial as defined by Elias, Proudfoot, Wakefield in. So this is the Kazhdan Lusztig polynomial of a matroid, in case you know what that is. So this, of course, makes sense only for geometric lattices because, this claim makes sense only for geometric lattices. Let me say that. The first part is true for graded bounded posets. So for all posets, G coming from the characteristic polynomial is always 1. So let me just say this. These results by Braden, Hu, Mathern, Proudfoot, and Wang imply that whenever you have a geometric lattice, this FST will always be a polynomial with non-negative coefficients. And the proof of that fact is quite hard. And that is not true if you do it for an arbitrary graded bounded poset. It's easy to produce examples of graded bounded posets. For example, having less coatoms than atoms, for which the KL polynomial attains a negative coefficient. The FST attains a negative coefficient. So there's no hope a priori. I mean, maybe you can extend the class of posets, but not to all graded bounded, of having a positivity result like what they have. Yeah, let us do a break, and then I will tell you what the F and G are for the polytopes and for the Bruhat case very briefly, and then I will define Chow functions and tell you an explanation of this cloud that I wrote in the beginning. Before starting, let me ask you if you have questions regarding the previous example or any other part of the talk so far. Good. Okay. So,
actually, sorry, quick question. Does this polynomial for matrix have combinatorial invariance?
Yes. That's immediate from the fact that the characteristic polynomial is combinatorial invariant. Yeah. Or the R polynomials of Bruhat, the intervals in the Coxeter group. That's open and conjectured since 40 years ago. So yeah, it would be amazing to see a proof of that. Yeah.
For Bruhat order, the left and right polynomials are same?
I mean the F and G? No, I don't think so. I think they differ. They are not similar. It's similar to the case of matroids, actually.
Yeah, but they are more symmetric.
But for
I think-
finite Coxeter groups, you can multiply by the longest element, and then it turns the left ones to the right ones.
Yeah.
It doesn't produce a new class of. But for infinite ones, I don't. Not sure.
Okay, so the point was the following. You give me a kernel, there are two special elements, F and G, called the Kazhdan Lusztig Stanley functions. F is the right one, G is the left one. In the case of graded posets, G is trivial, but F is exceedingly subtle. And actually, in the case of a geometric lattice, so a very restrictive class of graded posets, there's, there are various papers studying those polynomials called Kazhdan Lusztig polynomials of matroids, and there's a positivity result due to Braden, Hu, Proudfoot, Mathern, Wang. And yeah, that's what one can say so far about these things. Now let me move towards the second example, which was phase posets of polytopes. So if P is the phase poset of a polytope, then F and G are respectively the so-called toric G polynomials of ST and ST dual. So let me reformulate this. I won't get into much detail so in this example because it requires some knowledge about H vectors of polytopes and so on. But the key thing is that if you have any polytope, there's something called the toric G polynomial, the polytope. Every interval in the phase poset of a polytope will correspond to a polytope as well. So you can define this toric G polynomial for every interval. Well, that is precisely F. So the toric G polynomial is toric G is F, and G is the toric G of the same interval but reversed, which is the polar dual of that polytope. So, and yeah, these were introduced by Stanley, McPherson, and they were studied a lot in the late 80s and early 90s as a very cool application of intersection homology when it was defined. Yeah, so this is a very important example that
Does it also work for general Eulerian posets?
yeah, it works for any other posets, but the intersection homology interpretation is, I mean, has only to do with rational convex polytopes. So it's, but yeah, it does work. Okay, so this is another example. There are many questions regarding toric G polynomials, such as positivity questions and so on, that have been proved or are conjectured by various people like Gil Kalai and Karima Di Prasito and so on. So yeah, there are many results that involve these objects. So these are well-known objects by mathematicians. And yeah, I want to emphasize that they arise as Kazhdan Lusztig Stanley functions for an appropriate class of posets and an appropriate class and this specific choice of kernels. Now, the third example, if P is the Bruhat order on a Coxeter group, then F is, yeah, F and G are the Kazhdan Lusztig polynomials as defined in the original paper by Kazhdan Lusztig in 1979. Yeah, I won't give you too much detail about this because I want to focus on the matroid example, but so this motivates the name. So this is one reason I wanted to include this. There's another important object that has received less attention, though it's quite fundamental and very important in the case of matroids, which is called the zeta function, which in a sense tries to combine F and G. So let me define it quickly. Let kappa be a kernel. So I have some F and some G, which are the Kazhdan Lusztig Stanley functions. The zeta function associated to kappa is the element theta in I row of P given by theta equals G rev times F. So out of G and F, you do this operation and that's theta. And yeah, this satisfies many properties. So let me not write them and just say them. So the set of polynomials of every interval. So you give me the interval st, theta st is always a palindromic polynomial for any kernel in any class of poles. So theta is always like so if you want to be very precise, fact theta rev equals theta. So that is true. So that in the cases that I mentioned leads to three classes of polynomials. In the case of graded bounded posets, that's called the theta polynomial. In the case of convex polytopes, that was an open question, which I solved very recently. I'm writing that up. So the theta polynomial in the case of a convex polytope is the toric H polynomial of the antiprism of the polytope. Something that you can think of concretely. And in the case of Bruhat intervals, it is also called theta polynomial, and it corresponds to the Poincaré polynomial of the middle perversity intersection homology of Richardson variety. So there's a very nice geometric interpretation for theta in the three examples. That's the point. But I just want to define it, and let me keep writing the details of what this is and what it is. Okay, so that's the Kazhdan Lusztig setup, the Kazhdan Lusztig Stanley setup. And now let us move towards Chow. Chow, in a sense, is expected to be easier because Kazhdan Lusztig polynomials tend to be associated to singular objects, so Chow rings are very like and behave very much like smooth objects. So yeah, but let me give you the definition which will explain this this quote here. So first of all, lemma. If kappa is a p-kernel, then kappa is st. So this is a polynomial, and I can evaluate this polynomial in x equals 1. So if I do this evaluation, this is 0 for all s strictly smaller than t. So you can do this. So you can see that 1 is a root in the three examples that I showed you before. So for characteristic polynomials, if you plug 1, you are summing Möbius numbers, so it will be 0. For the kernel epsilon, for the Eulerian posets, that's obvious because the kernel is x minus 1 to something. So if you plug x equals 1, it's 0. And for R polynomials, that's something that it's a straightforward exercise if you're learning Kazhdan Lusztig polynomials. So well, this is actually something that you can prove very, it's very easy. It's just a straightforward induction. But with this in mind, so define the associated reduced p-kernel kappa bar by kappa bar at the interval st. Well, this will be kappa st divided by x minus 1 if s is smaller than t. So what this is saying is kappa bar will drop that 0 for all intervals that are like non-trivial. But of course, if you think about the characteristic polynomial, if you have the characteristic polynomial of a poset with only one element, that characteristic polynomial is always 1. So plugging x equals 1 will not give you 0, will give you 1. So you have to tell me what to do. So this division will not make sense if I put S equals T. And what you have to do is put -1. So, and this is somehow important. So I will explain why in a second, but you don't want to put 1 here. You want to put -1. So the reduced characteristic polynomial of a matroid is defined for matroids that are not of rank 0, let's say. For rank 0 matroids, the reduced characteristic polynomial is something weird. Well, the right definition should be -1. And notice that I'm denoting reduced with an overline, like what people often do when they work with the reduced characteristic polynomial of an arrangement. So rev stands for reversing and overline stands for reducing. Let me warn you that in early papers by Stanley, the overline stands for reversing, but that conflicts with the notation for reduced characteristic polynomial. So let me write reversing with rev and reducing with overline. Okay, so by definition, kappa overline is invertible because at every interval of length 1, I have an element that is invertible in the ring set X. So I can invert kappa bar. So definition, let kappa be a P kernel. The associated Chow function is the element H in the incidence algebra given. So H is defined as take your kernel, reduce it, invert it. You can do that because it's invertible because singleton intervals have -1s, and then change the sign. So if you think of the upper triangular matrices, what you're doing with this minus sign is guaranteeing that in the diagonal you will have 1s. So this will say that the Chow function at intervals SS will be 1. Yeah.
The kappa bar is not a P kernel anymore, is it?
No, it's yeah. This is like I don't know how to fix the naming here. Like I want to reduce a P kernel and obtain something. How do I call that? I say reduce P kernel, but that's no longer a P kernel. Yeah.
Okay, this kappa is always divisible by X minus 1. Did you?
Because of the lemma. The lemma is saying that whenever you have a non-trivial interval, 1 is a root. So you can drop that 0 for all non-trivial intervals. But for trivial intervals, you have to make a choice what to put because there's no. So what's the reduced characteristic polynomial of a matroid, of a uniform matroid of rank 0 or of a loop, for instance? You have to decide how you define that. And I argue that the correct definition should be putting -1. Yeah, and using that definition, so I obtain an element kappa bar in the incidence algebra, which I can invert, and this H is precisely defined in this way. Take kappa, reduce it, invert it, and then change the sign. That's the Chow function. Well, that claim here of inverting the reduced characteristic polynomial in the incidence algebra will be precisely that. That's the first example that I want to discuss in detail. So actually, let me write it as a theorem. But before that, let me just in the same way that I told you a few properties of the zeta function, tell you a few properties of H. So you can prove, or I mean, it is possible to prove that HST, so this is a polynomial. This is a polynomial that happens to put the variables slow. So the polynomial HST is palindromic, but the degree dropped by 1. So whenever you have a non-trivial interval, the polynomial HST is palindromic with respect to this degree. It's like dropping 1. And if kappa is non-degenerate, so the degree of kappa in every interval is what it should be, then the degree of HST is always rho t minus rho s minus 1 for all s smaller than. So HST has the correct degree and it is palindromic with respect to that degree, provided that kappa is non-degenerate. In the 3 cases that we have seen, kappa is non-degenerate, so you can think of this as being true. But there is no reason at all to expect that H exhibits any positivity property. Why? Well, a priori, we don't expect kappa to have any nice sign pattern, and you are inverting something here, and yeah, so there's no reasonable there's no reason to expect that H will have always non-negative coefficient. And in fact, there are examples in which you can give a poset, a kernel, and H is just something crazy. The same as the Kazhdan Lusztig polynomial. So if you give me some complicated graded poset, I can expect some Kazhdan Lusztig polynomial f or g attaining a negative coefficient. So the same happens with H a priori. Let me write that in case it's yeah. So there's no reason to expect Chow functions to be non-negative. So this is another fact that you have to have in. Now, we are ready to make a theorem out of that quote that I wrote in the beginning. So, theorem. Let P be a geometric lattice and kappa the characteristic function. The Chow function H satisfies HST of X equals a Hilbert series of the matroid towering of ST. So if you give me a geometric lattice, every interval is itself a geometric lattice, so it comes from a simple matroid. I can define the towering. Well, the Hilbert series of that thing is precisely H. So, corollary of that is that because of the Taylor package being true for matroid towerings, and because of hard Lefschetz in particular being true, well, the coefficients of HST are non-negative and they form a unimodal sequence. So let me write that. Corollary, this is a consequence of a differential of cats. HS, so let P be a geometric lattice and kappa equals chi. The Chow function is non-negative and unimodal. So this is a consequence of hard left sets, as I said, because whenever you have a ring that satisfies this property, you will have like a palindromic Hilbert series whose coefficients grow up to the middle and then decrease. So these two theorems led us to think, well, what happens if you don't have a geometric lattice? If you take a more general class of posets, say all graded bounded. We computed a lot of examples, and in all these examples, we always were seeing unimodal polynomials. I even mentioned this phenomenon to a number of people, and I asked them if they thought it could be the case that maybe these Chow functions are unimodal for any graded bounded poset where there's no Chow prior. And as it turns out, we were able to prove that. And actually, we were able to prove a much more general statement that I will tell you in a second. But yeah, before moving to that, let me give you one explicit computation for a Chow function for something that is not a geometric lattice. So, example. Let P be a chain on n elements. So your poset is a chain. That's never a geometric lattice when n is greater than 2. So you have a chain. You can define a characteristic polynomial and everything and do this construction. You will obtain some element h. What's this? Well, then HST of x is equals x plus 1 to the rho of t minus rho of s minus 1 for all s smaller than t. So chains have binomial numbers as coefficients in the Chow function setup. Of course, if you take a Boolean algebra or a Boolean lattice, that's a geometric lattice, so that will be the Hilbert series of the Chow ring associated to the corresponding matroid. So the first example is not geometric. The second, so let P equals the Boolean algebra or Boolean lattice. Well, results on torics of torics of uniform of Boolean matrix will tell you that you would expect this to be the H vector of the permutohedron, which is the Eulerian polynomial. So then HST equals the Eulerian polynomial R minus 1 Eulerian where R is rho of t minus rho of s minus 1. That's what you obtain if you do Chow functions of Boolean algebras or Boolean lattices. So in these two cases, you see the unimodality quite easily, or it's not difficult to prove that these are unimodal, but for general posets, it's a priori not clear. And yeah.
For the second one, like if I just use the definition, is this easy?
No. If you just use the definition of Eulerian polynomial, which is like counting permutations according to descents or exceedances, it's not obvious. But you can prove gamma positivity very elementarily. And yeah.
No, I mean like the fact that the Chow polynomial is the Eulerian.
Well, if you know that this is a Chow polynomial, then it is unimodal, right? Because the
Yeah, I mean, but suppose I just give you the Boolean lattice and I don't know what a permutohedron is.
Yeah.
Can I prove?
Oh, yeah, you can do induction, yeah. Because all the intervals in a Boolean lattice are themselves Boolean lattices. So you can do induction and prove a recursion that matches one of the many recursions that the Eulerian polynomials satisfy. So these are two examples that are very concrete in case you're interested. So one interesting thing is that I don't know what happens. So if you drop the second to last floor in a Boolean lattice, you will obtain the lattice of flats of a unifimator of corank 1. So I do know what the Chow function is in that case, but I do not know what happens if you drop the bottom floor. Like you drop the atoms and then compute this H. That is quite mysterious. I don't know the answer immediately. And yesterday when I was trying to compile nice examples, I realized that seemed to be doable, but not super straightforward. Okay, so this is a theorem that explains the name Chow. Now let me go back to the general setup. So I will have any poset and any kernel, and I will give you the main result that, among other things, will prove that for any graded bounded poset, so dropping the assumption of geometric lattice, this statement is still true.
Didn't you say that you have Chow functions where you found negative coefficients at some point?
There are examples, but they are like a little bit like ad hoc. Like you take a specific poset and some associated, some kernel constructed by hand for which this happens. Yeah.
So for the convex polytopes example, is this H the normal H polynomial?
So you want to know if I take the kernel equals epsilon and everything? Well, I will write that as a theorem. Actually, it is the H polynomial of the barycentric subdivision of the poset. Yeah.
How about the Coxeter example? We run this.
We do have a combinatorial description, but we do not know what's the geometric object. That's an open question that we leave in the paper. We do know what the polynomial looks like. And
negative?
It is non-negative, and it is unimodal because of the next theorem that I will write, and it is almost proved to be gamma positive. It depends on a conjecture by Villera and Brenti to prove that, but I think Villera and Brenti's conjecture is true, so gamma positivity should follow. And I think that even real rootedness might be true. So yeah, there's a lot going on. Yeah. Okay, so let's back to the general setup. So when I say back to generality, I mean any class of graded bounded posets and any kernel. Theorem. Let P or let kappa be a P kernel. If either the right or left ALS functions are non-negative. What I mean by this is that either f of every interval has non-negative coefficients, or either g of all intervals has non-negative coefficients, then h is non-negative and unimodal. So what this is saying is that, so take any example of a kernel, for instance, the three that I showed you before. If either the left Kazhdan Lusztig function, Kazhdan Lusztig Stanley function has some negative coefficients, or the right has non-negative coefficients, then the Chow function will have non-negative and unimodal coefficients. So in the three cases that I mentioned, so matroids and the kernel given by the characteristic polynomials, polytopes and the kernel given by x minus 1 to something, and Bruhat intervals and the R polynomials. In these three cases, the function f is non-negative. So you can conclude that Chow has to be unimodal. But what is very surprising is that I told you that in the case of a graded bounded poset, if you take G, that is always 1. So it's non-negative. And in particular, that implies that whenever you have a graded bounded poset, then the Chow function has to be unimodal, which is essentially like proving this statement without the geometric lattice assumption. So yeah, I can. Corollary, or
I'm confused. Which sheets are one for which posets you showed us before?
for the three examples that I told you before, so geometric lattices and chi, phase posets of polytopes and x minus 1 to the x of times, and Bruhat intervals of Coxeter groups with R polynomials. In the three cases, f is non-negative. In the first case, it's one of the main results of the singular Hodge theory paper. In the second case, that's a result on toric g-polynomials and intersection homology of rational convex polytopes. And in the third case, it's Elias Williamson's circles by modules main result. So there are three heavy results supporting that. Yeah. So in the three cases, you get unimodal polynomials. But before telling you the corollary, let me just mention one aspect of the proof that I find quite relevant. So how would you prove that a property of KLS functions implies a property of Chow functions? Well, one ingredient, I won't tell you the proof of just one ingredient. I will just sketch how to deduce the unimodality and non-negativity of H from the non-negativity of F. But the same strategy with some modifications works for G as well. So there's something that we call numerical canonical decomposition. So in the singular Hodge theory paper, June and collaborators have something called canonical decomposition of Chow rings and augmented Chow rings of matroids. Well, it turns out that we can make sense of the same decomposition for this general setup. So what this is saying is this. For every interval, you have this way of writing HST. So how to prove unimodality of H from positivity properties of F? Well, it turns out that the positivity of F and the bound of the degree imply that this fraction is non-negative and palindromic. And this is palindromic. You can assume by induction that this is unimodal and non-negative. So this is a product of two unimodal and non-negative palindromic polynomials. The same happens with this, and all these summas are centered in the same place. So this is, in a sense, like a very concrete way of thinking of one induction step in this big chart that you have. So yeah, of course, there are no graded modules here. It's just polynomials. So in case you are familiar with that paper, what this is modeling is the fact that the Chow ring of M is equal to something called intersection cohomology underline. I don't know how you actually call this. I mean, IH underline or Yeah, IH comes from intersection cohomology. The underline is some modification, let's say, plus the sum over all flats that are non-empty. I think you allow, yeah, of certain modules called K underline F. So these things depend on flats. So this thing, which is true for any poset, in the case of matroids, is just abstracting this decomposition called canonical decomposition. Yeah, and this ingredient is quite important because we use it in many proofs of positivity properties of Chow functions. Even though we do not have a definition of Chow ring, we do not have a definition of intersection of IH underline nor KF underline. So we believe this can be used also in the other setups to deduce what this should be, or what this has to be. So we don't know what's the analog of this in the case of hard polynomials in Bruhat intervals. Yeah, and let me write the corollary and so a corollary of the theorem if E is graded bounded and kappa is chi, then H is non-negative and unimodal. And the proof is one line. Apply the previous theorem plus the fact that G, so the left KLS function, is always 1, so it's non-negative. So you get the unimodality result. And well, that leads me to one more combinatorial result that I will just formulate. I will write it down very briefly. I won't tell you the details of the proof. The proof is quite hard, unlike this one, which follows from having like the correct recursion, which in turn follows from having the correct decomposition in the case of matroids. For this statement that I will write down now, I think one has to be very patient and very creative. And yeah, I mean, to us, one thing that was fundamental was an insight by Christian Stumm that I regard as quite surprising, like phenomenon. So let me start by writing a theorem that has to do with matroids. So let P be a geometric lattice and kappa characteristic function. Then H, so the Chow function is gamma positive. So in case you don't know what gamma positivity is, let me just say that it's a much stronger property than unimodality. So unimodality implies that the coefficients grow up to the middle and then decrease, in the case of polynomials. And gamma positivity, which is defined for polynomials, implies that the coefficients grow with a certain, like in a certain prescribed way. So it's like unimodality plus something more. To be very precise, what this is saying is that when you rewrite H in a different basis, you see some coefficients being non-negative. The proof of this fact uses the semi-small decomposition of Chow rings. But it's not clear how to extend this for an arbitrary great bounded poset because there's no Chow ring. Yeah. In fact, So example, if you take the poset given by this thing, so this is just some poset. It's graded and bounded. You can define H. You can prove that H01 is equal to x to the 4 plus 7x cubed plus 11x squared plus 7x plus 1. And this is not gamma positive. So for geometric lattices, you have gamma positivity. For graded bounded, you don't have gamma positivity. But there's a class in the middle called Cohen-Macaulay posets. And for those, we can prove that zero. So theorem, let P be a Cohen-Macaulay poset.
Is that like all the complex things when they're coded?
Yeah. Yeah. So every open interval has homology concentrated in top degree. If you have a Cohen-Macaulay poset and kappa equals chi, then H is gamma positive. And the proof is elementary but hard. Hard because it involves, so you want to prove that some quantity is positive, but it involves lots of alternating polynomials. So you have to expect that some miraculous cancellation happens, and it does. And yeah. And yeah, there is a conjecture that was posed by myself and Benjamin Schroeter that if, so yeah, if P is a geometric lattice, HST is always real rooted. And yeah, this is part of a family of conjectures of real rootedness in matrix theory. There's also a conjecture that the Kazhdan Lusztig polynomials of matrix are real rooted. And yeah, it turns out that we have tried to find some Cohen-Macaulay poset for which there is no real rootedness, and we failed so far. We even used posets coming from other constructions in combinatorics, like the famous counterexamples by Stanbridge to the Menger-Stanley conjecture. But all of these are real rooted indeed. So let me put this as a question. Maybe even for Cohen-Macaulay poset. I don't know. Maybe this is the correct setup for this question. And yeah, one more thing and I finish. So let me state this as a very broad question. In the case of a geometric lattice, you see a Chow ring. So you have an actual graded ring for which the Hilbert series gives you the coefficients of the polynomial. For graded bounded posets, it's not clear, but maybe there is some construction. And I want to pose that as a question, and I have some intuition of what properties such a thing should satisfy, because other properties of matrix Chow rings, like the composition by Matt Larson, have a counterpart that is true for Chow polynomials of posets. So yeah. So question. Is there a notion of, let me use this term, this is Chowish ring for arbitrary graded bounded posets. So if something like this exists, you expect maybe that this has to satisfy some version of hard Lefschetz. So if yes, is some, so do we have some hard Lefschetz for this Chowish ring? Another thing is that, so the property HST x equals 1 plus so this is true. So you take any graded bounded poset, take the polynomial HST, this is 1 plus the sum over all these things, over all the elements W that lie in the interval and have rank. So they are not covering S, that's the point, of the Chow polynomial of the truncation of this interval. So truncation means take the poset and erase the coatoms. And yeah, this is something that for matrix is not entirely obvious. In fact, I was very surprised when Matt proved that, because you rarely see like recursions that involve truncations of matrix for this kind of objects. But this is true for all posets. So by looking at the way Matt presents Chow rings of matroids, it looks like, since this has to be true for all graded bounded posets, whatever the Chowish ring is, yeah, it has to satisfy this. Maybe there's some decomposition at the level of rings that explains what you have, and therefore also this. And yeah, there's a natural guess that one can have on how to define this, which is essentially taking the paper by Wagner and Jusvinsky, taking the way they define the Grosvenor basis of the ideal. And you see there that you only see rank functions and not atoms at all. So I don't have any atomistic condition a priori, so I cannot use atoms. And using what Wagner and Jusvinsky have, if you plug, I mean, if you use that as the way of defining the Chowish ring, you will see that it matches all the cases that are relatively small and all matroids and many other examples. But for instance, for this thing, it doesn't work. So whenever you have a poset that has an element that compares to all the elements in the poset, for instance, here, you have one element that compares to everything. Of course, the 0 and 1 compare to everything, but typically in matrix, they are the only elements that have this property. So whenever you have an element in the center of the poset, so an element that compares with everything, that doesn't work. So I think that maybe working with Wagner and Jusvinsky definition of Chow ring and trying to give some role to these special elements that compare to everything, one perhaps could prove all of this in a more like categorical setup, working with a ring instead of just polynomial. Let me finish here. Yeah, thank you.
So you mentioned you can do something like deletion contraction for a poset.
Yeah. You can define the contraction by taking an element and just the upper, or the filter of the element. So that's like contraction. And restriction would be take an element, take the lower interval.
So Nick Profil has some refined version of this real rootedness, right? He says maybe the contraction and for matroid, the contraction and the original one, they interlace.
Okay, so it's true that he has many stronger versions of the real rootedness conjecture. One version that I quite like is that if you take the Hilbert series of the Chow ring of a matroid and the Hilbert series of the augmented Chow ring of a matroid, these two polynomials interlace. So I didn't have time now to tell you about the augmented story, but you can define augmented Chow functions. And I think that it is true that, or stands a chance of being true, that if you augment, if you take the augmented Chow function of a graded bounded poset, you have this cohomological, then these two things interlace as well. So
mouth contraction.
I mean, there's another conjecture that speaks about contraction, but I don't know about that one. I haven't tried that one in the general setup.
There's no notion of like a converse about main theorem.
Not quite because, well, for graded bounded posets, the main theorem is that if one KLS function is non-negative, either f with g, then h is unimodal. There's no converse of that statement because already for this example, like kappa equals chi, g is always one, so it's non-negative, but f, the KLS, the right KLS function, in general attains negative coefficients for graded bounded posets. So what you would expect is that if h is unimodal, then okay. Oh yeah, it could be true that if h is unimodal and non-negative, then either f or g is non-negative, though I honestly doubt that is true. Yeah. Because it would be like yeah, like deducing like positivity of these things from the that doesn't seem to work. No. Yeah.
So for Kazhdan Lusztig polynomials in this f equals chi setting, is there a description of the coefficients in terms of like flag?
Yeah.
Like for matrix?
Yeah, so the linear term of f is the number of coatoms minus the number of atoms. So that tells you that you can easily attain negative things whenever you have a poset that has more atoms than coatoms. So for instance, in that poset, you have one atom and two coatoms. So the linear term will be one.
But what about the rest of the coefficients?
It will be the same as for matrix. It will be, so for matrix, you have like these flag mini numbers. You can define the same thing for, it will work. Yeah.
I propose a guess for the Chowing of posets.
Okay.
I think in the realizable case, we should try something like the Chowing of an iterated blow-up of a projective space along linear subspaces.
Okay.
And these are very, very general objects, and quite possibly if you find the combinatorial model, it will be all the Chow functions. So maybe poset.
That would be very interesting indeed. Yeah.
So wonderful model, you have to blow up every intersection. Just drop that insertion
Okay.
and just forget about my Lusztig. So like inter.
Can you see for a chain? So for the poset in which like you have a total order in n elements. So it does work. Okay. Well, maybe it's a good candidate to try. Yeah, that would be amazing. I mean, we certainly regard this question that I wrote as like an important open problem in this setup because we lack an algebraic object to explain all these phenomena. So it would be amazing if this works. You had a question, yeah.
Yeah, in the case of matroids, this property you have for Chow functions comes from hard Lefschetz, and that's why you're looking for something that seems to have a hard Lefschetz.
Yeah.
Does Hodge-Riemann also give you something?
Well, there has been some speculation that maybe the Hodge-Riemann relations for Chow rings of matroids could explain some log concavity property for the Hilbert series of Chow rings. But so far, I don't think anyone has found a connection between these two things. Furthermore, I mean, the Hodge-Riemann relations hold an arbitrary degree, which, if you know about like real rootedness, implies that many matrices have like nice properties in their eigenvalues. There are some signs in the minors, if you want. And real rootedness is equivalent to the total positivity of some matrix. So one could hope that that is true, but then, yeah, one should use that this comes from a matrix in a very strong sense, because it's not true that whenever you have a graded ring that satisfies a full kernel package, the Hilbert series is real rooted. In fact, Chris found an example of, well, actually, if you take any uniform matroid like U34 and take the minimal building set, your Chow ring will have all the desirable properties of full kernel package, though the Hilbert series is 1 plus x squared, because it's not real rooted. So yeah, and I think we have an example of something that is not even log concave. So
Okay, this was our last meeting this semester. So it was a very inspiring and enjoyable experience for me, and hope the same was true for you. So be well until we meet next time. Yeah. Thank
Let's all thank the organizers.
Yeah.